today we shall consider one more topic, namely Linden-Meyer systems. These are very useful in creating pictures and in computer imagery. So, what are these systems? Linden-Meyer systems were defined in 1968 by Professor Linden-Meyer, who is a theoretical biologist. He was looking into the growth of organism, plants and other things, and how they could be modeled using a formal system. The formal language theory with the Chomskyan hierarchy was present at the time, and he changed the model and created a new model which is parallel in rewriting, and it could explain the behavior of the growth of organisms. So, they were defined L systems, because Linden-Meyer defined them, they are called L systems. They were defined in 1968, and in developmental biology the important changes that take place in the cells and during the development can be modeled by these systems. They provide a framework within which these aspects of development can be expressed in a formal manner. Now, the formal language theory point of view, L systems differ from Chomskyan hierarchy in three ways. In Chomskyan hierarchy, we saw that the rewriting is sequential. At any step, only one symbol or one substring is rewritten as something else. The left hand side is replaced by the right hand side of a rule, and only one rule is used at a particular step. But here in Linden-Meyer system, we consider parallel rewriting of symbols in every step. This is a major difference, and then we do not make any distinction between non-terminals and terminals here. The reason for this is when you try to model the growth of an organism, there is nothing like non-terminal and terminal, all symbols are equivalent. Whereas, from the parsing point of view, when you consider a natural language sentence, you have syntactic categories and the words generated by the language. So, there is naturally a distinction between non-terminals and terminals. So, here there is no purpose in having a non-terminals and terminals if you want to model the growth of organisms. But from formal language theory point of view, sometimes it is advantageous to have that distinction, and so later on we define extended L systems, where we make a distinction between these two categories. Not only that, in Chomskyan hierarchy we have always seen that the start symbol was a single symbol S. Even when we use regulator rewriting, the start symbol was only a single symbol S, which is noted as start symbol or the sentence symbol. Now, here the starting point will be a string that is called the axiom. Okay. So, with these distinctions, let us see how the system is defined. A 0 L system, 0 denotes without interaction. A 0 L is not OL, it is 0 L. 0 L system is an ordered triple V W naught P, where V is the alphabet. We are considering only one alphabet, and W naught is a string, it is a non-empty word over V, and that is called the axiom of the system, and P is a set of production rules. If they are without interactions, the rules are of this form. Left hand side you have a symbol from V, and on the right hand side you have a string. So, A belongs to B and alpha belongs to V star. Now, for each A there should be at least one rule with A on the left hand side. This is called the completeness condition, because we want to explain the growth for each and every cell of the organism. So, a cell can be represented as a symbol, and every symbol grows or changes, and that is denoted by these rules. Now, the relation is defined like this, the derivation step is defined. If A1, A2, An is a string over V, and the rules are given by Ai goes to Wi, then if you have A1, A2, An in one step, in the next step all symbols are rewritten simultaneously. A1 is rewritten as W1, A2 is rewritten as W2, A3 is rewritten as W3, An is rewritten as Wn. All steps take place simultaneously, all rewriting takes place simultaneously, and this is called one step of the derivation. Now, as usual we denote by double arrow star the reflexive transitive closure of W. The language generated by the system is defined as the set of strings which can be derived from the axiom. W belongs to V star, and from the axiom it should be possible to derive W. Take for example a system like this. You start with the axiom AB, rule for A is A goes to AA, rule for B is B goes to BB. Then starting with AB, you have A rewritten as AA, B rewritten as BB, and the next step each A is rewritten as AA, each B is rewritten as BB. So, in 2 steps you get this, and generally the string generated will be of the form A power 2 power n, B power 2 power n. The number of A's is doubled in the next step, the number of B's is also doubled in the next step. Now, on the left hand side you have a single symbol, and on the right hand side you have a string. The string can be epsilon free, and if it is epsilon free the system is called propagating. Now, if you have only one rule for each A, then the system is said to be deterministic. A 0L system pi which is equal to V W naught P is deterministic if for every A belonging to V there is exactly one rule in P, and it is propagating if it is epsilon free, that is epsilon is not on the right hand side of any production. So, you have a D0L system, you have a P0L system, you have a DP0L system which is a combination of deterministic and propagating. The language classes will be like this. If you have DP0L system, it will be contained in 0L system D0L, and that is contained in the general 0L. Similarly, DP0L will be contained in P0L, and that will be contained in the 0L. Consider one more deterministic propagating 0L system, where the alphabet consists of 0, 1, 2, 3, 9, left parenthesis, right parenthesis. One of the symbols 4 is the axiom. The set of productions are given by this: 0 goes to 1 0, 1 goes to 3 2, 2 goes to 3 within bracket 4, and so on. These are the rules, and with this in the first step if you have 4, second step you get 5 6, in the third step you get 3 7 5 8, and so on. So, proceeding like this in 9 steps you get derivations of this form, because look at the rules: 0 goes to 1 0 and so on, 4 goes to 5 6, and 5 goes to 3 7, 6 goes to 5 8. So, you see 4 goes to 5 6, second step you get 5 6, then 5 goes to 3 7, 6 goes to 5 8. So, in the third step you get this, and if you proceed you will get strings of this form. Actually, if you denote the integers to represent sort stem length, and brackets, within brackets you have the branches, then you have first step, second step, third step, and so on. Fourth step you have a single branch, then 2 branches you get, in the next step you get 3 branches, and so on. So, you find that the steps can be defined by the growth of a stem, and branches are developing from the stem, and this way the growth of a plant can be described. It is with this aim that Lindenmayer defined the system. One more example we shall consider. Consider the deterministic and the propagating 0L system, that is both deterministic and propagating, because you see that for every symbol there is only one rule. The symbols are 0 to 1 to 8, 0 to 8, 0 is here, and 3 more symbols, left parenthesis, right parenthesis, hash symbol. The rules are 1 goes to 2 hash 3, 2 goes to 2, 3 goes to 2 hash 4, 4 goes to 504, 5 goes to 6, 6 goes to 7, and so on. And the right hand side of the production is given in the lower row, left hand side is given in the upper row, and you start with P naught is equal to 1, the axiom is 1. If you use this, then you find that at the first step you have 1, then the next step 1 goes to 2 hash 3, then the next step you go get 2 hash 4, and so on. In the sixth step you get this. Now, in the n plus sixth step, for all n greater than or equal to 0, the n plus sixth step, the string will be of this form, Pn, Pn minus 1, etc., and in between you have these symbols. So, the development stages can be represented again as the growth of a plant and branching out. P6, P8, P13 are given in the figure, see the figure, P6, okay, we will see it later. The parenthesis expressions are branches whose position is indicated by the 8. When you have a 8, a branch will start from that position, and the branches are shown as attached on alternative sides of the main branch, and hashes are marked by vertical walls. Then zeros are marked with the slanting position, alternatively marked this way and that way. So, look at the string for P6, this is P6, then the string for P7, at the 7th instance you get this string, at the 8th instance you get this string. So, look at P6, the 2 hash etc. So, the hash is represented by a vertical wall in the stem or a plant, you can stem like plant, and 8 is where the branches branch out. You have a branch which is mentioned within the parenthesis. So, 1 is this, that is the branch is growing from this plant. Then the zeros are represented by oblique walls. So, you have between zeros 7, 6, 5, 4, the labels of these cells are given as 7, 6, 5, 4. Now, this is P6. Now, from P6 how do you get P7? These are the rules. So, 2 goes to 2, hash goes to hash, 2 goes to 2, hash goes to hash, 8 goes to 8, left parenthesis goes to left parenthesis, you see this, 1 goes to 2 hash 3. So, at this stage from 1 you get 2 hash 3, right parenthesis goes to right parenthesis, 0 goes to 0, but 7 goes to 8 1. So, at this stage you have from 7 8 1, 6 goes to 7, 5 goes to 6, and 4 goes to 504. So, the string obtained in the next step is this, and you see it is represented by a little bit grown stem like this. There are 2 8s, and when you have a 8, a branch starts. This branch which was earlier just 1 has grown like this, it has grown into 2 and 3, and another branch has started growing here, that is this. Now, this is P7. From this again by applying the rules, 2 goes to 2, hash goes to hash, etc., you get this string. 2 hash 3 will go to 2 goes to 2, hash goes to hash, but 3 will go to 2 hash 4. So, we have 2 hash 4, and 1 goes to 2 hash 3, again 7 goes to 8 within parenthesis 1. So, at the next instance you get this string. So, when you get this string, see that at the places where you have 8, a branch is started. So, the earlier branch has grown into this now, the earlier branch in the previous step has grown like this, a new branch has come at this position. So, the earlier branches have grown, a new branch has come, and this process is repeated. The branches themselves will start creating sub branches, and at the 13th step you have a very long string, and that represent a structure like this. You have the main stem from which you have the branches. The first branch has grown into this and it has developed 2 sub branches. The second branch has developed 1 sub branch and other branches have been generated and they have grown like this. So, a growth of a plant can be represented in this manner, and this was the main intention of Lindenmayer in generating this system or in defining this system. Now, the hierarchy within this is given by this. All DP0L languages are D0L languages as well and P0L languages as well, and they are included in the family of 0L languages. Now, from formal language theory point of view, the main interest in those days was to consider whether a new system is closed under operation, and especially 6 operations have been considered. They are union, concatenation, clean A closure, epsilon free H and sometimes ordinary H, intersection with regular set, inverse homomorphism. If a family is closed under all these operations, it is called a abstract family of languages. Now, we find that this 0L languages are not closed under any of these operations. Look at this language AA, which has got just 2 strings AA. Now, A alone is a 0L language. You can just have an axiom A and a rule A goes to A. This will generate only A. AA alone is a 0L language with axiom AA and the rule A goes to A. This will generate only this string. But when you consider the union has 2 strings A and AA. It cannot be generated by any 0L system, not 0L. This is not a 0L language. Why? We can have only one axiom. So, if I take A as the axiom, I should have a rule of the form A goes to AA to generate this, and if I have this rule, then from A I will get AA. I can still use the rule and get AA and so on. The language generated will be A power 2 power n and not this. So, this is not possible. Suppose I start with the axiom AA. To get A, I have to use the rule A goes to lambda, also A goes to A. So, from AA I can apply this rule for one A, this rule for another A and get A. But if I do that, again I can use this rule and get lambda also in the language, but lambda is not here. So, this way also it is not possible, and so this is not a 0L language. Similarly, you can prove that the family is not closed under any of the other operations as well. So, it is called an anti-AFL. This was the interest from the formal language theory point of view. In order to overcome that, extended systems were defined. We will come to that in a moment. The tabled 0L system was defined. What is a tabled 0L system? Actually, the motivation for this was to describe the growth of plants, mainly plants, any organism for that matter. And when you want to describe the growth of a plant, they may follow a certain set of rules during daytime, because in the presence of sunlight something happens and in the absence of sunlight something else happens. So, the growth mechanism may be different during daytime and it may be different during night. So, you may require two sets of rules to describe the growth of a plant. Also, the growth of a plant will differ during summer, during winter. Actually, they may shed all the leaves during autumn, and then in spring the leaves start coming, and in winter they only have stems. Such a thing happens. So, during different seasons different things happen in a plant, and the rules of growth will be different during each season. So, you may have to have different sets of rules to describe the growth of such a plant, and that is why we have what is known as a tabled 0L system. Lindenmayer defined this to describe the growth in different season and different time during a day. A tabled 0L system is an ordered triple like this, where it is denoted as a T pi, where V is the alphabet, W naught is the axiom, P is the set of tables. Now, each table contains rules of the form A goes to alpha, where on the left hand side you have a single symbol and on the right hand side you have a string. Each table will have at least one rule with A on the left hand side for each A belonging to V. This is called the completeness condition, and if you have only one rule, it is called a deterministic system. Now, suppose alpha is A1, A2, An, then from alpha you can derive beta by this. A1 will be replaced by beta 1, A2 will be replaced by beta 2, and so on. But all these rules Ai goes to beta I should be from the same table. That is, at a particular step you can use only rules from the particular table, where T is a table, only rules of the same table should be used at a particular step. Now, as usual, double arrow star will represent the reflexive transitive closure of this. The language generated is denoted as W. W belongs to V star, W naught derives W. That is, starting from the axiom you should be able to derive a set of strings. If W is derivable from the axiom, then W belongs to the language generated by the system. Consider this example. You have only one symbol A, which is the axiom, and two tables are there. In one table you use the rule A goes to A squared, in another table you use the rule A goes to A cubed. So, suppose I start with A, the next step if I use this table I will get A squared, if I use this table I will get A cubed. So, A squared also belongs to the language, A cubed also belongs to the language. Now, if I have AA, then there are possibilities like this. Starting with A, if I use one table I may get AA, if I use another table I may get AAA. Now, for this again if I use rule from the table A goes to AA, I may get AA, AA. I should use the same table for this A and this A. If I use the rule A goes to A cubed for this A, I shall get A. But I cannot apply a rule from one table for this A and a rule from another table for this A. I have to use the rule from the same table. So, if you look carefully, you will find that either the number of A's will be doubled in the next step or tripled in the next step. So, in general you will get a string of the form a power I, where I will be of the form 2 power m 3 power n. Again we can define deterministic systems, propagating systems and so on. Now we have tables. If each table has exactly one rule for every A belonging to the alphabet, then you call it as a deterministic system. If you do not have epsilon rules, then it is a propagating system. So, you have deterministic tabled 0L system, propagating tabled 0L system, deterministic and propagating tabled 0L systems. The main defect from formal language theory point of view is the non-closure under operations. Table 0L systems were also not closed under many operations. So, in order to make the system closed under many of the operations, the distinction between non-terminals and terminals was introduced. Actually, this is the one which creates the non-closure property. So, non-distinction between non-terminals and terminals affected the closure properties. So, from formal language theory point of view, extended systems have been defined, which make the families closed under many operations. Here we have two sets of symbols, terminals and non-terminals, or instead you consider the total alphabet and a subset of it as the target alphabet. Target alphabet corresponds to the terminals and the total alphabet corresponds to both terminals and non-terminals, or the union of terminals and non-terminals. So, a E0L system or an extended 0L system is defined as a 4 tuple V, the total alphabet, sigma the target alphabet which is a subset of V, and an axiom W naught, a set of productions P. Similar derivation steps are defined. At every step you have to parallelly rewrite the symbols. Then double arrow star is the reflexive transitive closure, and the language consists of strings which belong to the target alphabet. That is, from the axiom it should be possible to derive the string W, where W belongs to sigma star. If it contains a symbol which is not in the target alphabet, that string will not belong to the language. Again, within this also you can define tables, and so you have ET0L systems. For example, take this, start from S, S is the axiom, you have rules S goes to A, S goes to A goes to A. So, you start with this, you will get A, you start with this, you will get A, then you can apply this rule and no more strings will be generated. Now, S will not be in the language, the axiom will not be in the language because it is not in the target alphabet, but A will be in the language, A will be in the language, and so this is a extended 0L language. You see that earlier we saw that this is not a 0L language, but it is a E0L language. Now, so far we have considered systems without interaction. You can also talk about systems with interaction. What is interaction? On the left hand side you have A and a B. In a string A, B, C occurs like this. Towards the left of A, B, A occurs, and to the right of B, C occurs. Then B is replaced by W, that is, replacing B by W depends not only on B, but the left neighbor A and the right neighbor C. Something known as cellular automata is very similar to that. The state changes in a cellular automata occur like this. So, I will not go into depth in this system. So, a 2-0L system, everything depends on the left neighbor and the right neighbor. So, when you have a string like this A1, A2, An, on the left of A you have the environment. The environment is denoted by a dollar symbol, that is why you have one more component in the system. So, the first symbol, the rule will depend on the environment and the right neighbor. The second symbol, the rule will depend on the left and the right neighbor and so on. For the last symbol An, the rule will depend on the left neighbor and the environment. The rule will be of this form. So, A1 will be replaced by alpha 1, A2 will be replaced by alpha 2 and so on. So, you get from A1, A2, An alpha 1, alpha 2, alpha n, and the rewriting is completely parallel. The language generated again is the set of strings which are derivable from the axiom. Sometimes the growth of the plant cannot be explained in a proper manner just by rules without interaction, but if you have interaction or rules with interaction, then the growth can be explained in a much easier manner. Now, if you have just on one side the rule, it is called a 1L system. See, either you only consider the left neighbor or you only consider the right neighbor, it is called a 1L system. Again some examples are given here. So, the system has an axiom A, two symbols A B, rules are given like this. So, starting with A, you have dollar and dollar, and then you can replace it by A squared, A cubed, S cube B, etc. Then when you have a B, then the rule will be of this form, B can be go to B or B squared. So, this sort of a language will be generated by this system. The hierarchy between this and the class where 0L languages are included is given by this. This is the system. You find that 0L does not include some finite sets also. AA is a finite set, but it is not a 0L language, but some context sensitive languages like A power 2 power n are there. So, the class of 0L languages is like this, the class of 1L languages are like this, where this is the Chomskyan hierarchy. Some of these rules are like this. Consider this system, it is a deterministic system. Now, we will consider only deterministic system where you have only one rule for each symbol. You have A goes to A squared, then at the nth step you get A power 2 power n. The length of the string is given by 2 power n, and this is called the growth function in this case. So, consider this rule or this system. Initially you have A as the axiom, next step it goes to B, next step it is rewritten as AB, the next step A is rewritten as B, B is rewritten as AB, and so on. If you look at the length of the strings, this is 0th step, first step, second step, and so on. The length of the string here is 5, it is the sum of the previous two steps. The length of the string is 8 here, which is the sum of the length of these two strings. So, you see that the length of these words are just Fibonacci sequence, Fibonacci numbers. And if you look at this one, you find that the sequence generated is A goes to A, B, C, C, then again replacing A by this rule, B by this rule, C by this rule, you find you get this. The lengths are 1, 4, 9, 16, and so on. They are squares of the natural numbers. Similarly, if you consider this system, the sequence generated is this, 1, 3, 6, 10 etc. The length of the sequences are 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4 and so on. They are called triangular numbers. The length of the n string will be sigma I is equal to 1 to n. Now, another system is given like this. If you look into the length of the strings, it is 1, 8, 27 and so on. The length of the words are cubes of natural numbers. The whole thing can be explained in a convenient manner. Let me take this particular example. The axiom is A and the rules are like this. So, the lengths of the sequences are given like this. Now, the Parik mapping of a string is like this. Parik mapping. Suppose I have a string AAB. I will take the alphabet here. Some string AABCB, CAB, something like this. The Parik mapping of this is denoted by this. It is a vector where the elements of integers. The first one denotes the number of A's, because I assume the order A, B, C for symbols in sigma. The second denotes the number of B's, the third denotes the number of C's. So, in this example it will be number of A's will be 1, 2, 3, the number of B's will be 1, 2, 3, the number of C's is 2. So, the Parik mapping of this string is 3, 3, 2. Now, this idea if you use, you find a connection between matrix algebra and this. M is a n by n matrix, where n is the size of the alphabet. It is a 3, ABC is 3. So, it is a 3 by 3 matrix. The order is A is first, then B is second, then C is third. So, if you look at the right hand side for the rule A, B, C, C, the rule for A is this, and the number of A's on the right hand side is 1, 1, number of B's is 1, number of C's is 2. The Parik mapping will be 1, 1, 2, and that is the first row. The second symbol is B. The Parik mapping of that is 0, 1, 2, and that is the second row. For C, the right hand side is C, the Parik mapping of that is 0, 0, 1, and you have the third row. The Parik mapping of the axiom is given by this. M is known as the growth matrix, and if you have a column vector eta which consists of just ones, pi m eta is pi multiplied by m, then by eta, it gives you 4. That is what you get in the first step. This is the string and this is the length of the string. The second step, the length of the string is 9. If you calculate pi m squared eta, that will be 9. So, in general at the nth step, the length of the string is given by pi m power n eta, and you can specify the growth function in this manner, making use of the Parik vector for the axiom and the growth matrix. Now, the growth function, if it is polynomial bounded, it is not malignant. If it is not bounded by a polynomial, it is called malignant. Then the use of L systems is really in computer imagery, not only describing the growth of the plants, you can describe a picture and also generate beautiful pictures making use of L systems. You have to only write a few rules and then specify the number of iterations, and you can get beautiful patterns. 3-dimensional objects also can be modeled using this. Now, the description of the string is captured as a string of symbols. An L system is used to generate the string, and then the string of symbols is viewed as commands controlling a logo like turtle. You can have 2-dimensional or 3-dimensional turtle. The basic commands used are move forward by drawing a line, make a right turn, make a left turn, etc. Line segments are drawn in various directions specified by the symbols to generate the straight line pattern. Since most of the patterns have smooth curves, the positions after each move of the turtle are taken, and the control points, they are taken as the control points for B-spline approximation or B-spline interpolation. That is, the position after each move of the turtle are taken as control points, and B-spline interpolation is used to draw a smooth curve. This approach is very concise. We will see with some examples. You can generate beautiful fractals using this. In general, the position of the cursor turtle is denoted by 3 points. X y are the x y coordinates and A is the orientation of the cursor. Then if you move through a distance delta, the step size is d and the angle increment is delta. So, from one point if you move through a distance d, then the new position will be x dash y dash a, where x dash is given by x plus d cos a and y dash is given by d sin a, y plus d sin a. A line is drawn between 2 points x y and x dash y dash. Suppose you denote f, then it may represent the command to the cursor move forward as above without drawing a line. Small f may denote move forward a step length of d by drawing a line. Plus may denote turn the turtle left by angle delta. So, the new position will be x y and then angle will be incremented by delta, that is anti-clockwise rotation. Minus may denote the corresponding clockwise rotation. So, with this you find that you can interpret a string and then draw a picture. For example, start with this rule, with axiom, with this axiom and rule like this. For f we have a rule, f goes to f plus f minus f plus f plus f minus f. Of course, I have not specified the other rules, plus goes to plus, minus goes to minus. So, if you look at the axiom, look at it carefully again, plus f plus f plus f plus f, and if f denotes draw a line of unit length and plus denotes turn anti-clockwise through 90 degrees. What does the axiom denote? It denotes f plus, plus means turn, f plus f plus f. So, you draw a square. Now, you use a rule like this. So, in the axiom each f will be replaced by this string. Then let us see what we get. The first f, when you replace it, start from here, f plus f minus f minus f f f plus f plus f minus f. From this to this, replacing one f you will get, then again turning anti-clockwise through 90 degrees using a plus. From this to this position you will have another f replaced by the string, then again from this to this position, and the last f will be replaced by this. So, you find that at the next stage you get this one, and in the next stage you will get this one. If you want to draw a smooth curve, it will become the coast island. Consecutive positions of the turtle can be considered as control points specifying a smooth interpolating curve. B-spline interpolation is used for most of the column patterns. Column patterns are those patterns which are drawn in front of the house, especially in South India. Every morning in villages, nowadays towns or cities have only flats and they do not have enough space to draw the patterns, but in villages even today every morning you will find that the ladies spray water and use rice flour to draw beautiful patterns in front of the house. That is taken as a daily routine, and those patterns can be very easily generated using the L systems using B-spline interpolation, and just one or two rules. For example, this is a column pattern. This is called Candice or Mittai Patlam. Actually, the first stage you will get only this one, this pattern. Actually, there should be some more dots also which are not marked here actually. This is the first one, and then when you combine 4 of them you will get this picture. Then if you combine 4 of such pictures you will get this. Again 4 of this can be combined to form a bigger pattern. So, starting with one axiom which is this and a rule of this form. 4 rules are there. Rule for D is this, then for C is this. A and B will be replaced by such strings, and in the next step again you will use similar patterns. You find that if you specify the number of iterations you will get beautiful patterns in this manner. Of course, successive points are joined by smooth curve using B-spline interpolation. Now, plant structures can be generated and you can get beautiful imagery, computer imagery using this. For generating living organism like plants, the 3-dimensional turtle is used. A 3-dimensional turtle is different in some aspects compared to the 2-dimensional one. In the 2-dimensional one you have the x coordinate, y coordinate and the angle orientation. Here you have the x, y, z coordinates denoted by p, that is a position vector which gives you the x, y, z coordinates. H, L, U give the orientation of the turtle. Then W represent the width, and you can keep on changing the color also. So, C represents the color in which the lines have to be drawn. So, a 3-dimensional turtle has other parameters like width and color. So, for generating plant like structures some special systems are used making use of a 3-dimensional turtle. The special systems are stochastical systems. So, with each rule you attach a probability. See, the growth of the plant is not identical. Suppose you sow 6 seeds, all the 6 plants will not grow in the same manner, there will be slight difference, and that sort of a thing is captured using probability. you attach some probability with the rules, and that is called a stochastic system. Brackets are used to separate the branches, that we have already seen. You use brackets so that the branches are separated, and sometimes you use a different type of a bracket so that you want to move to something and draw, then come back to the same position without drawing anything. You use a different type of a bracket. Then in stochastical systems, as I told you, probabilities are used. Also cutting, and then cutting a branch, and when you cut, how the branch grows, all these are captured in computer imagery when you want to describe plants. Another example is this, again f plus f plus f denotes this. Then if you use a certain rule, you get another column pattern like this, which is called a snake pattern, snake column. See that the first one, if you use spline approximation, you may get this, and then the second iteration when you use, you may get this. This one kept 4 times is this, and then beautiful patterns like this can be generated. Some leaf pattern, the growth of a plant like this with stems and so on. Here the same plant may not grow in a similar manner. So, if you use probability, different types of plants can be got, and also you can have by cutting that the string, this is represented as a string, and then the symbols in the string are interpreted as move of a cursor. So, if you cut this, remove a portion of the string and then use the growth, the plant may grow in a different manner. That can also be captured using L systems. So, we find that L system is a different model from formal language theory point of view. The main difference is parallel rewriting of symbols in every step, and then you can interpret the symbols in a string and use it for computer imagery. In 2 dimensions, you can have fractals generated, you can have column patterns generated, and in 3 dimensions you can have plants and other structures generated using this system. Not only this, even music can be generated using this. In fact, we have tried to use this to generate some music. You write some sort of a tables for each symbol. There are 7 swaras, sarigama padani, and for each one you can write a rule in a similar manner and have tables, and apply these tables in some particular order and use a sound generating device along with that. You can generate some particular raga, some sort of a tune in that raga. Thus, L systems can also be used for generating some music, not necessarily voice or anything, but some sort of a instrumental type of a music can be generated using this. And theoretically, it is a different form always, it is a different form, and then formal language theory point of view, the study has been interesting. Some of the problems related to this, that is given 2 deterministic 0 L system, whether they are growth equivalent, whether they represent the same growth, was remaining as a whole as an open problem for a long time, and finally it was solved. So, this is another topic which is of interest, and recently there is something like Watson-Crick 0 L system that is also being explored. So, this is another advanced topic which we are considering.